First of all, let me thank the organizers for the opportunity to present my results at this conference. This work is joined with my colleague Katerina Halina, and we consider the following control system on a half plane. X1 greater than 0 and x2 in R. T is on the segment 0T. We consider the standard heat equation. It is the Laplace operator, and we have a boundary condition with a delta function in it. Delta function we consider with respect to the second variable, so with respect to x2, x1 is equal to 0. Also, we consider the initial condition and the end condition. Here, if we take a look to this problem, it seems it to be overdetermined, but because we have the condition 4, the end condition, but we have a parameter u. It is the function of the class L infinity on 0T. And the problem is to choose this parameter, this u, such that our system drive the initial condition to the end condition. It is one problem, and the second problem is it is if the first problem is not solvable, we can try to drive the initial condition to the neighborhood of the end condition. We try to construct a sequence of controls U such that these controls approximate the desired end condition. And if we take a look at the boundary condition, we can see that it's not non-standard and has the delta function, or direct distribution. So this control is pointwise, and pointwise control is a mathematical model for sources supported in a domain of very small size with respect to whole domain. If we try to imagine how the solution might look like, we can see it in these pictures. If we put the initial condition 0 and u is equal 1, so it is 0, and here we set u equals 1. We see that at the small time, we have the following plot of our solution. Then the time groups, we can see that the graph is changed. Also, we can see that really the solution depends on the not only of x1 and x2, and we can represent it as a function of the modulus of x. And this we can use this condition play a focal role in our research. The controllability problems of the heat equation were studied both in bounded and unbounded domains. Where most of the authors studying these problems deal with domains bounded with respect to spatial variables. Some names of others we can see on the screen. At the same time, there are quite a few papers considering domains unbounded with respect to spatial variables, and we can see the names of others who investigate these problems. Pointwise controls, as I have said, is a mathematical model of the solid supported in a domain of various mass, small size to the whole, whole domain. That is why studying control problems under pointwise control is an important issue of control theory, and some mathematicians studied these problems. The main result of the present paper is rather similar to our previous paper. However, the methods of obtaining the results are essentially different in these two papers. Roughly speaking, we deal with the two-dimensional case, studying reachability set and constructing the solutions to controllability and approximated controllability problems were in the paper I mentioned above. But in this paper, we reduce the two-dimensional reachability set to the one-dimensional reachability set and deal with the one-dimensional case, studying these problems and constructing the solution in the present work. In addition, the method used to study the one-dimensional reachability set is in this paper principally differ from those used for two-dimensional set in the paper mentioned above. Moreover, some results of the present work have not analogies in the mentioned paper. Denote R plus the set from 0 to plus infinity. G of R plus is a space of infinitely differentiable functions on R whose supports are compact and they contained in R plus. Consider also the following Sobolev spaces. Here is the standard Sobolev space and standard norm for it, and for the spaces with negative indices, we consider the adjoint space with a strong norm. Also, for m from -2 to 2, we denote by h hat m of R squared the subspace of all distributions or functions in Hm of R squared that are even with respect to x1. Evidently, this new space is a closed subspace of Hm R squared. Also, we consider the Sobolev space on R plus times R. It is the subspace. It is the space with additional condition that derivatives with respect to x1 equals 0 when the order of derivatives is from 0 to s minus 1. And the appropriate norm also we consider, and H minus S is the joint space with the strong norm of the space. As I have mentioned, the significant role in our decision, in our study, plays the functions depending of modulus of x. And we consider not simple modulus and modulus squared. So if f belongs to L squared, L2 of R squared, and let f equals g of modulus of x squared, where g is the function on R plus. If we set x1 equals square root of R cosine of phi, x2 equals square root of R sine of phi, R belongs to R plus, and phi from the segment of the from 0 to pi, we can obtain the following relation. So the norm f can be represented through the norm of G. And this correspondence f and g, this correspondence f and g can give us the operator phi, and we can also consider the space L. F from L2 of R squared, such that there exists G from L2 R plus, such that f of x equals G of modulus of x squared. So this operator acting on f give us G according to this rule. This operator is invertible, so if we have a function G, we can obtain a function f, and this operator phi is an isomorphism of L and L2 of R plus. L is a subspace of H0 hat, and subspace of L2 of R2. L is a Hilbert space with respect to the inner product in L2 of R squared. Also, we have that this scalar product can be represented through the operator phi. The norm of phi is 1 divided by square root of pi, and Fourier transform of L equals L. We can also represent the Fourier transform operate phi through Fourier transform by the following rule and sorry, we can introduce a special operator phi acting from L2 of R plus to L2 R plus according to the following rule. And this operator can be represented according to the following formula, where J0 is the Bessel function of order 1, and we also can see that this transform is a modification of the well-known Hankel transform of order 0. And for the operator phi, we have the following properties. Phi is invertible. The inverse of phi equals phi, and phi can be represented by the following formula. Also, we consider the value of distribution at the point 0 according to the following rule. So we consider, in fact, we consider this value as the limit when the first argument of f is multiplied by alpha, and alpha tends to 0. To study our problem, we use even extension for all our functions in our problem, and we can reduce our system to the following system. This a control system. Here we have a new summand in the right-hand side of our equation. This summand is generated by a boundary condition. Roughly speaking, the jump to delta 2 multiplied by u at 0 in even extension of our function gives us the term in the right-hand side of our equation. So now we can consider definition for controllability and approximate controllability. First of all, we for t greater than 0 and w from h hat 0 of r squared denote by rt of w0 the set of states wt from the same space for which there exists control u in L infinity of 0t such that there exists a unique solution to system 9, 10, our new system, such that the end state of our solution equals wt. Further, we consider system 9, 10 instead of system 1, 3 because they are equivalent. And definition. A state W from our space is said to be controllable to target state WT for the same space in a given time t if WT belongs to reachability set for W0 R. We can say that R is the reachability set. So we want to drive W0 to WT by the help of the control U according to system 910. Another definition is the definition of approximate controllability. Here we want to steer, we want to drive our initial condition W0 to an arbitrary neighborhood of WT. Evidently, for each neighborhood, we should choose an appropriate control U that depend of this neighborhood. Using the Poisson integral, we obtain the unique solution of system 910. It has the following form. And we can split this solution into two summands. The first of them depend on the initial condition, and the second one depend on the control. Sometimes we consider not only controls from L infinity, but controls bounded by a given constant L. And we denote this set by U TL. Also, we can represent our reachability set using our formula for solution, and we can see the following formulas. We have some properties of our solution. The first part of our solution that depends on the initial condition belongs to h hat 0 of r square for each t, and for t greater than 0, we have that this part of solution is infinitely differentiable. And if W0 belongs to L, so if it's have representation through modulus of x square, then the solution has the following the same representation. And if we also have that the second part of our solution belongs to L and has the following estimate. We have obtained the properties of reachability sets if we the main properties is fourths and fifths. So we can reduce condition of belonging to reachability set at point G to belonging to reachability set at point 0. According to this formula. So now we can concentrate it on the reachability sets at the point 0. Using the operator psi, we can build reachability set both RT and both RLT. It is obtained as the image of appropriated set for the operator psi. And put yu psi of wu. Yu of rt has the following form, integral form. It is obtained from the form of wu, and we can obtain the form of reachability set both RT and both RTL in the following form. Since psi is isomorphism of L and L square of R plus, we can state that the closure of both RT equals psi of closure of RT of 0, and the analogous relation from R8. And now we study these new reachability sets. We can say that if G belongs to both R TL, then this function has the following estimator. This estimator can be obtained directly from the representation for G, and using the exponential integral here, and estimators for this exponential integral. Also, we can say that if G belongs to both RLT and G capital equals phi G, then G capital can be extended to an entire function GE for the less than not greater than 1 and type not greater than t, and has the following estimate. This estimate is obtained also directly, and we can show by example that condition 23, this condition is only necessary for G belonging to G to belong to R both LT, but is not sufficient. However, if G satisfies condition 23, phi G can be extended to an entire function of order not greater than 1 and type not greater than t. We can have a look to theorem 9 and can see that this condition is necessary for G to belong both LT. We have the following theorem. If G belongs to L2 of R plus, G capital equals phi G, and condition 23 hold for G, then G capital can be extended to an entire function GE for the not greater than 1 and type not greater than t. And that condition 23 is not sufficient for G to belong both R TL, but it guarantees the necessary condition from theorem 9 for phi G. We can also give necessary and sufficient condition for G to belong RTL via solvability the infinite Markov power moment problem generated by G. So if G belongs to L2 of R plus and condition 1 to 3 hold for G, we can denote a sequence gamma n by the following rule. And then we can say that G belongs to both R TL if and only if there exists U belonging to UTL such that for all n from which n is natural or zero, such that this condition holds. Here we have the Markov power moment problem generated by the sequence Gn, and we want to find U from this condition. If we consider a sequence of finite Markov power problems, we obtain sufficient condition for G to belong both R, LT, closure of this set. So under the condition of previous theorem, if we reach n capital natural number, there exists un from U or TL such that these conditions holds. Then G belongs to closure of both R TL, where closure is considered in L2 of R plus. And the main result of our work follows from the theorem 13. We have the closure of RT equals L2 of R plus. And we can formulate the conditions for controllability that follows from properties of both RT and both RTL. Denote W0T, the difference between WT and W0 of T. And first consider conditions for controllability a necessary condition for controllability, or the conditions that F, sorry, it is this should not be here. Let W0 belongs to H hat 0 and WT belongs to H hat 0 too. L greater than 0 and T also. W0T defined by the condition 29. And if W0T belongs to RLT of 0, that is the state W0 from H hat 0 is ULT controllable to the target state WT in the time T time T. Then W0T belongs to L and have the following estimator. The next theorem is also necessary condition, and it's analog of condition for R bolt. Also, we assume that condition of previous theorem is true, and denote F capital Fourier transform of W0t. G capital is Fourier is psi of f. Then G can be extended to an entire function GE of order not greater than 1 and time not greater than t. Moreover, f can be also extended to an entire function fe, and fe s equals g of s1 squared and plus s2 squared. And fe is of order not greater than 2 and type not greater than t. In addition, we have the following estimate. We have an analog theorem that gives necessary condition for R boot, but I have no sufficient time, and I consider the following theorem. If we consider W from H hat 0, WT from H hat 0 also, and W0T defined by our formula, we can define omega n according to this condition, and then we can state that WT belong to RTL of W0, that is the state W0 is UTL controllable to the target state WT. In the time T, if and only if the following Markov of our power moment problem is solvable. If we consider a sequence of finite Markov power moment problem, we obtain the sufficient condition for the state W0 is approximately controllable, approximately UTL controllable to the target state WT. And now we will consider controls from L infinity of 0t, and we will consider approximate controllability. We obtain the following theorem. We have RT of 0, closure of RT of 0 equals L. Here the closure is considered with respect to the norm of H hat, sorry, it is 0. It is 0. And from this theorem, we obtain the following theorem. State W0 from H hat 0 is approximately controllable to state WT from H hat 0 in a given time t if and only if W0t belongs to L. And also we have the following statement on the lack of controllability to the origin. So, if we consider arbitrary W0, we cannot to drive the state to 0 if W0 don't equal to 0. So if state W0 is controllable to the state WT, that is equal to 0 in a given time t, then W0 equals 0. And
dear Dr. Fardigola,
I see. Thank you for attention.
thank you so much.